Sure.
So really
Okay,
pleasure to have Alfio Borzi, who will talk about some kinetic models, optimal control for some kinetic models. So thank you again, Alfio.
Yes, thank you very much, Nader, and thank you also, Mohammad, who also contacted me. And I'm very pleased to give this talk. Well, it's now the time of the online talks, but hope to see you in person sometime. So you asked me to talk about the Fokker-Planck equations. But since I'm following, say, my own research, direction or idea that involves also kinetic models, I would like to give this talk in this more general context, but part of it will be focusing exactly on Fokker-Planck equations. So the idea is here to define a different or say new way to formulate optimal control problems that are perfect, that are appropriate for kinetic models in a general sense that I'm explaining. So I hope you see my slides. Now I will, and the first problem is how to move to the next slide. I don't know this. Can you help me in this, or is, I don't know how to do it. I'm sorry, I don't know how to do it. Stop here. Stop. It's very strange. Where is my... So this is... well, this is a problem now. Can you see my slides now?
No, we can't see your slides. No.
Can you tell me how to move forward to the slides?
Can you use your left and right arrow keys? The arrow keys.
Yes, I've used them, but
okay. Try and open your slides again. If they're closed, open them again.
Oh no, they are open. Yes, yeah. Yeah. Well, I try again to share.
Are you using a PDF? What format are you using?
A PDF. Yes, PDF. Okay. It's a PDF, and this is a preview. So let me try again.
So you're on a MacBook?
Yes, yes.
Okay.
I guess if I share desktop would be better, but let's try again. Yes. Okay, let me do in a very practical way. Do you see the slides?
Yes.
Okay, so I'm enlarging them and I keep staying on this format. Is okay?
Yes, it's okay.
Perfect. You should make it larger because I cannot see, say, myself in this sense.
It's good. What we can see is perfect.
Okay. Okay. So the framework is, follows a long tradition started with Boltzmann. The idea is that if you have multi-agent systems or multi-particles, system with many degrees of freedom, and you want to describe it, then you will focus on probabilistic or material density that does not give the exact state of each of the particle, but it gives it in a density way, which would be probabilistic meaning or material. And in this case, in all models where you have such kind of description, then the governing model is a kinetic model. Now, my focus is, since actually we know a lot about simulation of these models and also theory, the point is what we can do with this. So at any application, then we will come to the point to define optimal control problems. So we'll rely on our knowledge on optimal control theory. And my proposal is to consider ensemble functionals. So this is why we will call it ensemble control problems. Okay, so let me see just what we can do with that. So in my, say, long-term research perspective, the idea would be to control plasma and or design systems that confine plasma. And I've already contributed in things like collective motion or stochastic modeling, which is in fact what we will do with the Fokker-Planck equation. And here there are other applications that coating has not been my topic. It could be, so this is related to Fokker-Planck, and space propulsion has been a collaboration work with a company in Luxembourg with Boltzmann equations. So this is the main frame for this work. And I would like to put it in a general perspective. So in principle, I mean, since the very old times, we come to macroscopic models as PDEs as saying the underpinning of microscopic models. Microscopic models can be deterministic. This is all Newton mechanics. So this would be a system of ordinary differential equations. But in more recent time, we have extended this to stochastic models, and stochastic models include drift, diffusion, and jumps. And much less studied kind of stochastic process is a piecewise deterministic process. This is processes that are deterministic for time intervals that are defined also randomly, and then change dynamics. And actually, all these are connected in some way. So let me show you just two pictures. On the left, we have a drift diffusion jump model, and this is just a few realizations. You see 4 realizations. So imagine we actually should have infinite realizations of this model. And in this case, it would be impossible to discuss each of them separately. This is why we are going to do approach with density functions. On the right-hand side, we have a piecewise deterministic process. So also in the deterministic case, we also have infinite many trajectories if I take, say, a distribution of initial conditions, or if I don't know the initial conditions exactly and I have some uncertainty in this part of the deterministic mode. So in all cases, we will have this kind of need to move from the microscopic description to a density function description, which is actually what was proposed by Boltzmann many years ago. So in that case, it was about material density. And supposing you have a deterministic model, as we had before, so x dot is ax, and you have a distribution of initial conditions modeled by f0, so this is the initial function, the initial condition, then we can trace all these particles moving for some time with these dynamics. And in fact, the density, evolution of the density for this model is described by the Liouville equation. In fact, the name Liouville equation is due to Boltzmann. And so you see we have a hyperbolic model is a conservative transport equation with this initial condition. And the point is that the Liouville equation is the basic model for essentially all kinetic equations that we know. So it's the ground where we build our kinetic equations. And in this way, we have what we call a statistical description of this model. So just to show you what I'm going to do, I would like to put a control function on the drift, which is the drift is actually what is determining the deterministic evolution. And why I'm doing this? Well, let's consider this example. Suppose a very simple dynamics. X dot is the sinus of x. This is nonlinear dynamics. And we start with a Gaussian distribution of initial conditions. Then you see that the drift, the sinus of x, is actually minus the gradient of a function. In this case, is the cosinus of x. So what happens to this model? Well, the model starting from the Gaussian distribution will evolve in such a way that the density will concentrate in those parts of the domain where the potential has minima. So in some sense, you see already that there is a way to control this density by constructing potentials where the minima is where you want to go, where you want to concentrate your density. This basic idea is what we will do. And one way to construct such drift is, for example, this one. So it is, as you see, in this case, I put two controls, U1 and U2. And I have a part, A0, that would be your uncontrolled dynamics. Maybe it's some smooth vector field. And then you may think of adding a control that shifts this vector field in time. This is U1. But you also can imagine to have a bilinear part, a part which modulates the term x, so a factor x in this term. So it seems very mysterious, but there are many reasons to do this. The first of all, in control theory for ordinary differential equations, the first U1 would be called a linear control, and the second will be a bilinear control. These are the essential controls that appear in engineering. But a more, say, interesting way to do this is to recognize what happens to the moments, because now we have a statistical model with a given distribution density. We can think of average and of variance. So the average for the state of the system is this function m of t in the bottom of the slide. And you see it is just the average of the position, if x is a position. And this is our first moment. The second moment, the variance, would be the deviation from the mean of all possible states of the system. Now, if I just work on the Liouville equation, doing integration and starting from a Gauss distribution, I obtain equations for these moments. And these are given here by m dot equal to U1 plus m U2, and V dot is 2V U2. So you see that the first part of the control is going to control, to drive the mean. Whereas for the variance, it is the second control that is affecting the variance. So it is like this X is concentrating density or is enlarging density. Okay, based on this idea, we can define a control problem, because I've now told you the control mechanism. Though the other part is how to define the objective of this control, the purpose of this control. So I like to show this picture, just we are used since 1,000 years. If you want to control the flow of the water, you put a channel where the density concentrates. So this is essentially the idea of ensemble control functions. If you have a trajectory that all particles should statistically follow, let's say xd, and maybe at the final time you even want to be somewhere else with some point xt, then you define attracting potentials, or say valleys, that have their minima exactly in the points where you would like to be. So the function are to be minimized, in the sense that the purpose of my control would be to concentrate the density, and so the trajectories close to this minima point, this minima trajectory, which is our desired one. And this leads to defining the functional jf of u. And you see theta, you can imagine it, these are attractive potential. For example, the minus of a Gaussian, no, they are reverse one. And if I minimize this functional, it means that if we should concentrate on the bottom of this potential, where the integral will be smaller. And this is the part concerning tracking and terminal observations, the phi t. Obviously, you don't want to achieve these goals at any cost. You actually have some limitations, so you have to invent ways, criteria to keep the cost of your control small. And this will be a part of the function to be minimized as well, and it can have many different structures. So now I show you about this definition of the cost of the control. So now we are in a regime where we have only time-dependent controls. Later we will see also in space or space-time. And the standard way to write the cost is the L2. So L2 of the cost of the control is whatever is omnipresent everywhere in the control theory. But you may have also other requirements. For example, that your control is not changing too much during time. This means that you don't need to manipulate your system every time, and also with jumps, but you would like to have something continuous. So this will be achieved taking a H1 norm. And these two correspond in the cost function given at the bottom of the slide. So it's the first one is L2 and the last one will give H1. It is quite new to also consider L1 control costs, which is the part in the middle. And these kind of norms, the L1 norm, will induce sparsity. Sparsity in the sense that the control will try to be small as much as possible in the time interval. And this is why we can call it minimum action control. Okay, so now we have defined completely the functional, and we have our model. We started with Liouville, and now you see I have the formulation of an optimal control problem. So the optimal control problem is formulated as minimizing this ensemble functional. You may say, why not the average in the control cost? Well, this control is depending only on time. So if you even put f integrate in x, if f is constant, is kept the total density is constant, then the integral in x will be just 1. So it will not be any change. And this is an optimization subject to a constraint. The differential constraint is the Liouville equation put here. So then you can also have a lot of more features like requiring that your control has pointwise restrictions, like this kind of box constraints defining the admissible control you have. So example control problems are a source of infinite new problems. And I would like to tell you about this. What are the problems? Well, first of all, you are forced to study the theory of your governing model with a control function that may be not differentiable. So some theory may be not existing, although in the Liouville case, starting from Lyon's works, Deperne, etc., we have a lot of result on this field with Liouville equation or continuity equation, as the Ambrosio school. Then you would like to prove that the map, fixed initial condition, you fix the control, you have a state, a solution of the Liouville. Change the control, you have another state. So you have a map, just call it control to state map. And we need to prove this is Frechet differentiable to obtain the optimality system. And continuity, however, is enough for this map to prove existence of at least one control. Uniqueness in these cases, you almost never achieve it. So as just an example, so as in any optimization problem, as you know, if you take the Lagrange framework, so you can characterize your minimizer as the solution of an optimality system. Now, this is actually the point of Lagrange function where the derivatives are all zero. So in this kind of framework, of Lagrange framework, you obtain an optimality system, which is the Liouville equation with a control, an adjoint equation, which looks like a transport, which actually is a transport equation, but with the right-hand side and with some special terminal condition. So this equation is running backwards. And then you have a variation inequality that characterizes the control function. So this kind of problems are much more complicated than when only look at one of these equations. And they are the challenge of analysis, theoretical and also functional analysis and numerical analysis and computation. And I will try to tell you more about this coming soon. So anyway,
sorry, I have a question.
Yes, please.
I didn't understand if this attracting potential theta and fear are given data from your physical model, or are two functions that somehow you choose also?
Yes, are two functions that I choose, just that they work as attracting potentials or valleys. In fact, there is no unique choice.
Okay, so but you fix them and you don't treat them as a control.
No, they are just like you fix the trajectory, they are just extending the trajectory that is what you wish in the ensemble framework.
Okay, but the point is that you are not even interested in the dependence of the control to state map with respect to these two potential.
No, the control to state map is not related to this potential. It is just the map for the governing model. So if I choose this control, what is the state of, what is the density? So this is not related to the choice of the function. You see the valleys, the potentials come in the adjoint equation.
Yes, but it says like if I change the attractive potential, I change also that map.
No, absolutely not. I can remove in this system the adjoint and the variation equality and just think of the problem, what is doing f independence of u. So you can be anything in the space, say h1 0t or whatever. No? So this is independent of the function. But the solution of the optimal control problems obviously depends on these values, on the choice. Did I answer your question?
Yeah. Okay, thank you.
Okay. So let me go and see what are results that have been achieved. So one is to analyze this problem on weighted subwoofer spaces, because just now I linked to your question, the point is your functional must be integrable, right? So in classical theory of ODEs, the theta will be a quadratic function. But if I have an integral of theta f in Rn, this may be not integrable. So to guarantee that this integral is well posed, I will take something like a Gaussian, inverted Gaussian, okay? And if I want a quadratic functional, then I have to work on subwoofer spaces with weighted norms so that I can guarantee this integrability. So this was part of work. Other results about theories, existence of controls, and differentiability of the map. Numerically, we need to solve the forward model, the adjoint model, and for this have been analyzed some methods like the stability conserving Runge-Kutta, Kurganov method for the hyperbolic part transport or conservative transport, and also strong splitting for the source terms. So all this has been analyzed and proved in L1 norms. And this is just about the optimal system. But then we have to solve it, and solving it means applying numerical optimization schemes. And in one of these works, we have developed a semi-smooth Newton method, but many other methods that can be done, can be implemented on this. Okay, so the Liouville equation is the simplest, but the most intriguing because it comes, the Liouville equation comes everywhere in kinetic theory. And to move a little bit towards kinetic theory, I thought to discuss with you another problem. So the other problem would be, say, a Vlasov model with collision, or if this collision term is quadratic, would be a Boltzmann. So as you see, the part on the, I don't know if you see my marking the text. So if you see this part, the part on the left of the governing model is a Liouville equation. It looks like it is not in conservative form, but it is because we are thinking of a Hamiltonian system actually, no? So, but in this case, it is just because V does not depend on X, is are independent variables, and U does not depend on V. So this is a case where the control is only space dependent. So in this case, you would like to design a control field, not time dependent, that controls your system. This is something close to the idea of making confinement of a plasma. No, you want to fix this control. The right-hand side of this model is a collision model, and I will show you now one simple one on the next. And in this case, it would be, we are in a phase space, so we have space coordinate and velocity coordinates. And in this, if we are working in a physical box, then we need to define boundary conditions, and a nice choice for application is specular reflections. So these particles are bouncing back from the boundary of the box, maybe without losing energy and keeping the total density constant. So in this case, again, I can define an ensemble functional. Now we are in phase space, so the valleys will depend on X and V, if you want. This is the beauty of these works. You can modeling everywhere. So it depends on what are your ideas, what are your targets, what you would like to achieve. And U is now a function of X. The cost can be taken, for example, an H1 in space. So this would be our ensemble problem for a kinetic model. And the kinetic model, the challenging kinetic model is one with the collision. In general, collision will have two parts, a gain-loss structure. And I like very much to work with the Kelso-Storer model that allows to approximate many different situations. So Brownian motion, strong collisions, and in this sense, it is a connection to the Fokker-Planck equation I will discuss later, okay? So if you use this, now the question is to construct adjoint models, solve this problem, and my work in this field is, say, in progress, because my wish is to go to multi-species Boltzmann equations. That was the collaboration with the company, but we have actually no theory for that. In fact, many of these problems have never been considered before. Even for this simple collision term, we realize that the adjoint equation is not in gain-loss form. So we need to invent new methods to accommodate these new equations. But we have already results like Poisson control to state map, existence of optimal controls, and so on. At this point, I just would like to mention that the one big challenge is to do optimal control of kinetic models in a Monte Carlo framework. I mean, in the field of kinetic models, like rarefied cases where you actually cannot use as deterministic differentiation scheme, different numerical scheme. Okay, so now let me somehow start the second part or the other part of the discussion, which is the one that leads us to the Fokker-Planck equation. So in this case, we have one particle, say, or one agent that is subject to a stochastic dynamics. So if we may consider all realization of this model, then we'll get again many trajectories. And we would like to describe this by a probability density function. And as you know, the way to do this is by defining a conditional probability density and essentially constructing the Chapman-Kolmogorov equation. And from this Chapman-Kolmogorov equation, by saying how this conditional probability density works for the special stochastic process, we derive our differential models. Okay, so by doing this, and here again we are repeating another line of development in science, which starts with Einstein. By doing this, we obtain again the Liouville equation. If we have a conditional probability where you have the exact connection in trajectory. But if we have now a diffusion term, then, I mean, we have a Brownian motion, the background, then we'll have in addition a second order differential operator, which is our diffusion operator, right? If you have jumps, then you have an integral part. So you see, this is a source of an infinite number of models. Many of them are also new or not so much considered. And this, in general, we say we have partial integral differential equations. And I would like to say this equation that I'm showing you here, you see we have the Liouville equation, then we have the diffusion part, which is like an unbounded collision operator. And we have another term, which is this jump. All this is referring to this many evolution, many realization of the same model. But you know, from statistical mechanics, there is equivalence. If, for example, if you have not interaction between the two points of view, so we can think of the material density also as a probability density function and the other way around. Okay.
Excuse me.
Yes.
Please. For the kernel, you said that this is the jump process. So I mean, for the particle case, what does mean? You have some particle, how they jump, or how you explain this term?
Well,
I mean, the kernel.
Well, this is not. I'm not thinking of a particle in this case, but if you think of a model in finance, this is the case where you have at Poisson times, you have an event that asks you to choose a sides, so a jump sides, and the sides is given by this function g, and so the model is doing this jump at this time. And this is at the level of a single realization. If now we look at the density function of this process, so for all possible realizations, then this is the term that takes care of the jump part. So lambda is the rate. I mean, these times, the Poisson times is an exponential distribution, tells you when to do the jump, and the sides is chosen by G. Did that answer your question?
Okay, thank you.
Oh, okay, we are welcome. So, so I say, there are many names here. There's Einstein, Smoluchowski, Fokker-Planck, Kolmogorov, etc. And for the piecewise deterministic part, we have, again, a system of Liouville equations, and then a connection of the different densities by a stochastic matrix. So, and this goes on infinitely. So I like this as a source of many, many interesting problems. And the point is now, can we think of controlling these models with our ensemble framework? So you see, in principle, if this is the evolution of many trajectories, and this case is the, say, classical Fokker-Planck equation, then I would like to put a control in the drift, or maybe also in the diffusion, to drive these densities in some way, okay? We have also the point that if we have a stochastic process, we can ask to limit this by some barriers, and barriers in the stochastic process correspond to boundary conditions for the Fokker-Planck equations. And also here, I would like to show you why we think that controlling the drift is actually driving the density. Well, actually, it is intuitive, but let me take again the example that I did at the beginning. So we have a deterministic model will be x dot is sinus x, and now we have some Wiener process that makes is a stochastic model. We start again by a Gaussian distribution and let this model evolve. You see that the evolution is going to put the probability density on the bottom of the valleys of the potential that is giving this drift. So this is the idea again. We can control these probability densities by controlling the shape of the drift. And in this case, I thought to give you an example where you have now a control that depends on space and time. So we have all three cases. And for this, I took the case of a motion of a pedestrian. This is one of the topics I like to consider. So imagine a pedestrian in a room. So we have barriers, and the pedestrian cannot go out. So we have reflecting barriers, which means for the Fokker-Planck equation, you have zero flux boundary conditions. In fact, the Fokker-Planck model that I'll show you before can be written in a flux form. No, so the flux zero boundary conditions just the standard formulation that we have. Now you see that the control is going to be the drift. It is actually the drift, and it depends on the state itself and on time. So this is actually so-called a Markov control. In fact, is what I would like to construct is something that, depending on the state where you are, gives you the right u, which is the velocity field where that is, say, driving the pedestrian. So we are very close to what would be a feedback control. The point is now for me to show that thanks to the ensemble approach, it is possible to derive a purely feedback control, and so making the link to the integral-Bellman equation. So let me show this. So what is the ensemble control? Well, now we are in an unbounded domain. In principle, I can take my valley to be a quadratic function, okay? So I have integrability of this functional, and I have my average functional or ensemble functional, where again, I've constructed some valley, okay? And I have decided to consider as L2 cost of the control. And in this case, I cannot forget about the density. So I mean, the control must be also taken in the average sense to have it as a statistical meaning for the entire function. So you see there is an average in theta, but also in the u square. And then we have some final observation function. Again, we have now an ensemble functional, maybe adding also some abysmal set, and the governing model is the Fokker-Planck equation, because I need actually to write this ensemble and I need to use the density function. So I'm not working with the stochastic differential equation, but I'm on the level of the probability density function. And by doing this, there is here again in the background, there is a lot of work done for proving existence of solutions for the forward equation, etc., and existence of control. Then there is all the numerical part I will mention later. But what is important for me at this point is to just show you the optimal system, just using the Lagrange formalism, but also here we can use the Pontryagin formalism. So what I obtain is the forward model is again my Fokker-Planck equation, and the adjoint model looks different from what we would expect with the standard control of partial differential equations, because we are using this ensemble function. So you see that in the adjoint, you have even the control, the quadratic, the part, which is the cost of the control, okay? And yeah, I think here there is a mistake. Yes, I'm realizing only now. The adjoint equation is so the Neumann boundary condition is just the derivative of P equals 0. I'm sorry, these two terms, theta and the diffusion part.
The equation before.
Huh?
I think these two terms, it's in the equation before.
Yes, in fact, I realized something now. By copy paste, I make the wrong paste. Yes. So this is part of the adjoint equation, okay? And if I look at the derivative of the Lagrange function with respect to the control, I will get optimality condition that actually will be f times nu gradient of p, okay? This variation equality. But this is actually, because we have a parabolic model, we have the guarantee that the density will never be 0 in any open set. So, and will be always non-negative. So I can just take this as a sufficient condition for optimality. And this brings me to the Pontryagin principle and to the formulation of the Hamilton-Jacobi-Bellman equation. So if I go to do this step in a more elegant way, let's say that the stochastic process starts at some point x0 at time t0. Then, as you know, our ensemble function is exactly the expected value functional used in stochastic control theory, and the functional j on the optimal trajectory is the value function. The value function, considering the control problem with the state starting at x0 at time t0. So this is our value function. And what is to remark here is that if I write the Hamilton-Jacobi-Bellman for this problem, I exactly obtain the adjoint equation that I had before, P with U satisfying this sufficient condition. So in other words, the AGB is the adjoint equation in the optimal trajectory, and the adjoint variable is the value function, okay? So in principle, I've told you of open control in the sense that function U depends only on time. So this will be this stochastic model. This is what we discussed with Liouville at the beginning. And with the last case, we have discussed a closed loop problem, where the control depends on the state, on the real state of the system. So I've done some experiments to see what would be a difference. So what we are trying to do is like approximating with some open loop control function a closed loop one. And well, these are examples where you see on the top, you will see the closed loop case. You see that the control is more effective in keeping the trajectories, but it requires a very large effort in computation with respect to an open loop control where you only compute time-dependent functions. And this is in the bottom, you see this kind of control, the effectiveness of this control. It is actually a very good one, depends now what is your target. So this is the case where you then compute the controls, and now you switch off your PDE problem and you take these control functions, which have been computed, and you make a kick on what should be the trajectory. So like you take an initial condition in a place which was not considered as the desired trajectory in our computation of the control functions. And then the question is, how is the model behaving? Is the closed loop control doing better than approximation with open loop? Well, yes, in fact, you see on the top again, closed loop, the control will bring back the system on the right trajectory and then follow it. And this is a little more difficult for the open loop control. Okay, so there are many results in this field from the theory to the numerical analysis. There are many requirements in the numerics that should be taken care of, like the fact that the density cannot be a negative function. And it is quite challenging to get high order scheme with this property. And then there is all the issue of constructing numerical optimization schemes. Gauss-Newton, the Newton method is one, but recently I've put a lot of effort in constructing new methods based on the Podryagin maximum principle. Okay, there are some reference. I will give you the slides if you ask for. It would be my pleasure. And I've talked, if we have still 5 minutes, is it possible to tell you about Nash games?
Yeah, that's okay.
Okay, so the pedestrian is one case, but actually in general, we would like to move from standard optimization. I think this is also the next challenge, from standard optimization to multi-objective optimization, to multitasks, and this leads us to game theory in many cases. And a nice development with the Fokker-Planck was to consider the problem of two pedestrians that have different targets, and to reach their targets, they would collide. And collision is not a good thing. So I investigated together with my friends, my colleagues, the problem of making solving the collision problem, to get avoidance without giving a mechanistic idea like particles with potential that may interact or whatever. It's just purely the solution of a Nash game. So what is this? It is about having two players, which means in our case, two pedestrians with two control fields. So we have two controls with the two different functionals associated to them. And the idea is how to construct this functional. Well, the point is, what is collision? Collision would mean that the overlap of the two density of the two pedestrians will be as large as possible. No? So avoidance is just try to minimize this part, this kind of functional, and we can obtain this say, heuristic or almost rigorous way, constructing the probability that the two systems are overcrowded. They are closer than some distance are. So this is this kind of functional will be the functional that will tell us how close are these two pedestrians. Okay. And again, we think of two controls. We can have continuous control. So the pedestrian is not jumping somewhere with an L2 function, but it's some continuous function. For this is enough to take H1 0t because of embedding, you have a continuous function. And therefore, we have, for each of the two players, a functional which has the structure in the middle of the slide. So let me tell you about this. So here we have no trajectory. We do not prescribe trajectories, but just the wish of each player to get to a final position at final time. So this is the first part of the functional. Then we would like to have their velocity to be h1 in time. And then we would like that all these pedestrians should minimize the possibility for collision, so to get avoidance. Each of these pedestrians is therefore modeled by a stochastic differential equation, which is the drift, it is the control, and some perturbation due to many reasons, okay? Correspondingly, we have two Fokker-Planck equations. They are not linked together on space because the two stochastic processes are independent. The dependence is here on the level of the functional. And now a Nash point would be one of equilibria because there are no more minima. Here there is only a concept of equilibria, something very interesting. And the Nash point would be that the first player would optimize with respect to his coordinate and the other with the second. Okay, this kind of formulation leads to a structure of each functional of this type. So there is a part which is depending all on the player and this common part of collision. And it was very beautiful to realize that after we did all this modeling, that we can construct a functional for both players that is not the sum of the two, because you see here, the sum of the two will be a factor 2 in W. Here, it is not. And we prove that it is very easy that if the pair U1, U2 bar is optimal for the control problem, then this must be also, is one of the possible Nash equilibrium. And there have been many experiments of this. Okay, I'll jump about this proof. We can go on it later. And it was nice to do compare results of this setting with with the Nash equilibria with Fokker-Planck's, with the results from psychology, behavioral psychology, where people are really asked to go from one point to another and avoid collision. And this is the setting of the experiment. And this was the result with the Fokker-Planck Nash game. One can see that one of the two players, or say one of the two pedestrians, is slowing down or accelerating to avoid collision with the other. It's a very beautiful result. Okay, this what I wished to tell you about my work on this field. Thank you very much for your attention.
Okay, thank you. Thank you very much, Alfio. So are there questions?
Yes, I just would like to comment that the slides there are another 30 slides attached, which are more technical about the theoretical work and numerical work, but I thought this would cover the picture.
Okay, so that's for the next hour, right? That's for the next hour.
Would be, but I think
for those
1 hour is enough.
Okay, so yeah, are there questions?
I have a question.
Yeah, okay, Mohammed, yeah, you can go.
Yeah. My question is more about how to prove, I mean, rigorously, if there is some result, how to show, how to pass from a microscopic model to mesoscopic model, for example.
But this is the research program. Yes, this is the research program that started with Boltzmann, and it is part of a lot of work of many people. I would say, especially in France, there are the entire school of Lyons is working on this. There is also Gallagher. There are many people who work about deriving mesoscopic models from microscopic, considering spherical balls, non-symmetric balls, or ions. This is one very big chapter of kinetic theory.
But I mean in particular case, for example, for pedestrian or not in.
Well, no, because if I say that a pedestrian is modeled by a stochastic Ito equation, then it is already done that this model is, the probability density function of this model is described by the Fokker-Planck equation. So this is already classical work. Yes, yes, yes. I mean, there are many ways to derive it from. I mentioned the Chapman-Kolmogorov equation because it's the most elegant way to do it, and can be in many different ways.
Okay.
Yeah. So maybe I have a question, maybe it's which is related. So, for instance, like in a pedestrian, I mean, there is a macroscopic model, like Hughes model. Maybe you are aware of this model.
Yes,
but
yes. Yeah.
I was wondering, how is it related to the model you showed us? Like, can you?
For the avoidance, or for
Yeah.
the simple? Well, the point is that I mean, if we talk of the avoidance problem, which is the one I like very much, many of these models are mechanistic models. It means you have the pedestrian and you attach to it some physical laws, like a repulsion potential. So if you don't touch this, because the potential will go to infinite, like Morse potential. So in some sense, pedestrians have been made like particles with physical laws, so that if they come together, you have a scattering theory, or you have just a simple collision theory of Newton, and you do things like this. My way is completely different. I don't want to say that people follow physical laws when they meet. I also don't think it is true. And I just let them make the game. So the people will just try to avoid to get the equilibria, the best, say, trade-off between what they want to reach and what they should avoid to do. So the game approach is completely different for the model you mentioned and all the other models that are being considered in this field. Yes, I think it's much more elegant and makes more fun. Yeah.
Okay, can you go back to your to the model? To your
from the Fokker-Planck for the game.
Okay. Now, this one here, you have two people, right? So you have two individuals.
Yes.
Right. So if you had only one individual, then there's no interaction. Then the person will just go in a straight line.
Yes, because I even thought to say which trajectory. So you will go straight line to the final point. Sure.
Yeah. So here you are really trying to just understand the interaction of two particles.
Yes, exactly as we do by walking. Yes. Yeah.
Yeah. So this is, I mean, in a sense, this is different than like Hughes model is more like a model for a density, right? So it's a model where already you have some density of pedestrian and and here now the interaction between the two people is modeled by what precisely? I'm trying to see where.
This is the point. It's not modeled. This is the point. It's not modeled in the function.
But you have VP is what? VP.
WFP. You mean this? This?
Yeah. So you have W and VP. W and VP, these
Yes,
they
it is
take
this
into
one.
account. Okay.
It is the functional that tells you how close the two pedestrians are. This is not material density. We have really only two pedestrians subject to stochastic law. So there is no physical interaction. And I personally...
But okay, now, this model, in a sense, you did it for 2, but you can do it with 20 or 100.
Yes, yes. We can be a crowd, yes. We be also mean field variation, formulation of it, if you like. If I would have time to do it, among other things, would be nice to do a mean field case. But yes, but the essential is this one. So we have no...
Yeah, but you think now that mean field game thing will give you the Hughes model? I mean, can you set it up so that you get Hughes model in this limit, or some other...
no, I don't think it gives. No, I don't think it gives a Hughes model. There is, there will be always no interaction, direct interaction, because the point is this: if you have direct interaction between two pedestrians, then your Fokker-Planck equation will be 4-dimensional. Okay, so if you have n pedestrian, you will have 4n dimensional, which makes, I mean, it's not tractable at all. Yeah, this approach, the Fokker-Plancks are all independent. It means you will get n 2-dimensional Fokker-Plancks. It's very easy in comparison. And the interaction is about their wish in the functional, given in the functional, to avoid collision. Yes. So it's very interesting other point of way. Yeah.
Okay, are there other questions? Any questions or comments or no? Okay, so who wants to stay for the next hour to go with 40 more slides? Okay, I think no one.
I don't think, but I send you the slides, and if you have any question, we can always contact.
Yeah. Thank you. Thank you very much. Thank you very much.
Thank you.
You're welcome. Thanks for asking me to give the talk. My pleasure.
Yeah. Thank you. Thank you all.